So we had already done the first step on number 10. I'm going to, well, let me finish reading the problem here. So we have found the $500 per month invested at 5% compounded monthly for 20 years. So what happens is this person is now going to switch accounts. They're going to take the money that they just had and they're going to place it in their new account. And then they're going to start putting $1,000 per month invested at 8% compounded monthly for 20 years. So let's do a new share here. Let's get a whiteboard. So here's what we did on Tuesday. So that's the number we came up with on Tuesday. So after the first 20 years, this person had $205,516.83, which in terms of a retirement is not a lot. Does anybody know kind of what the recommended number is for retirement? Because I don't think we talked about this last time.
Like the recommended age before you retire? Isn't it like?
So the age right now is like 65-ish. But what's the recommended dollar amount that you retire with? And this is actually for my generation, so it may change for you guys because, of course, of inflation and all that. But does anybody know what the recommended dollar amount is currently that you retire with? And this is going to be super depressing. The recommended dollar amount is $1 million. So experts think that you should have $1 million saved up by the time that you retire. Now, of course, there's a couple of things that come into play with this. One of the things is, if you've got things paid off, so if your house is paid off and your car and every, credit cards and all that's paid off, you don't need $1 million to retire. But if you're still paying on things, the recommended amount is $1 million. So yeah, retirement's not looking super good for me right now. Yeah. Okay, so we have gotten this amount in this account. We want to switch this account over to, or switch this money over to a new account. So our new account, and I'm going to switch colors here. Our new account says that we have a rate of 8%. So our R is going to be 8%, so 0.08. We are also doing this account for 20 years. So our time is going to be 20 years. Our number of compoundings, I believe, was monthly again. So our N is going to be 12. And so now we have this situation. So the formula that I used originally here was a monthly payment system, right? So I'm putting money in monthly. Can I use this formula, this big pretty thing right here? Can I use this formula for this $205,516.83 that I'm now going to deposit into the account? And guys, I need you to talk to me on this one because this problem shows up a ton. I love this problem. And this is actually a really common occurrence. Most people do not work the same job for years on end. That used to be like my parents worked the same job for 30 some years. That's not the case anymore. People switch jobs. I have switched jobs. I have switched states as I've switched jobs. So what happens is people will build up different retirement accounts in different places, and they'll want to take that money if they can, they'll switch it over. So one of my accounts actually is an optional retirement plan that I took in South Carolina. So that money goes with me wherever I am. So I can take my money if I want and switch it over to North Carolina if I wanted to do that. Now I haven't done that because I like my money being stocks right now. So that's kind of what this person has done. They've either switched a job or something has changed in their life where they kept their money in this particular account for 20 years and now they're switching accounts. So they have made this $205,516.83 over the course of the first 20 years. So now they're going to take all of that money and they're going to dump it into this new account that has 8% interest, which is really nice. We're doing it for 20 years and it's 12 months, compounded 12 months, or 12 times a year, monthly. So, but there's another piece of information that they give me on number 10. And that other piece of information that they give me on number 10 is that she is going to make, or she or he is going to make $1,000 per month payments. So in this case, we could say that Big R is going to be $1,000 per month. So how do I fix this? Andrew, I believe it is. I think it's the future value. No, hold on. Let me get it right. It's the future value of an ordinary annuity. That's the formula. I never remember the names of these things. So when we say annuity, that's a savings account of some sort. That's either a savings account or like a retirement account. This isn't like a mortgage payment or anything. So what am I going to do, guys? I'm open to suggestions. Somebody, anybody, talk to me.
Do you add the 1 and the 0.5 over 12 and raise them to the exponents?
Okay. So I like where you're going, Andrew, but this is where I have the issue. So this money's coming with me, right? But then remember, this formula also has a payment amount here. So when we go to do this new account, how much are we paying per month? Because originally we were putting in $500 and now we're putting in how much money?
1,000?
Yeah, we're putting in 1,000. So somehow I have to take this amount here, this $205,000, put it in this new account while still adding $1,000 per month. So how do I reconcile these two different amounts here?
Would you set them equal to each other?
Well, if I set them equal to each other, that means that I'm saying I'm only going to get $205,000, right? And I don't think that's the case. I think that I should end up with more money than what I have here, right? So if I put money into an account and let it start moving, like start compounding, I should have a bigger amount than what I started with, right? Unless, of course, your money's invested in stocks, and then that's a whole different story.
Yeah.
So let's do this. Let's say that we're going to the new account. So let's say that we have this $1,000. I could find how much money is in the account by the time with that $1,000 included, right? By using that future value of an ordinary annuity formula. So let's do that. So I am going to do the same exact formula here. I'm going to have S equals 1,000 this time. Oh, that's a terrible 1,000. So 1,000 times 1 plus 0.08 divided by 12. Now this time it's going to be raised to the, actually no, it's the same thing, 12 times 20, right? Because we're doing it 12 times a year for 20 years again, minus 1 over 0.08 divided by 12. Does somebody calculate that out for me and tell me what you get? Has anybody got an answer for me?
I got 161.67.
Addie, that sounds a little off. And the only reason I know that that sounds a little off is notice here on the other side, see how we got $205,000 here with a lower APR and a lower amount here? So this one should definitely be a higher value.
I got $589.
Okay, Andrew, keep going. You got $589.
And 2 cents, I guess, for rounding to the nearest cent.
Andrew, you're very close. Something is wrong with the way you typed it in, and I'm wondering if you put 8% in or 0.08.
0.08.
Okay, then something, did you multiply by 1,000? Because you've got that 1,000 up front there.
No, I did not.
So multiply your answer by 1,000.
$5,800, $5,089.20, or I'm sorry, 589,020 and 0.4156.
So 42 cents. There we go. So guys, that's how much money that this person is making by putting $1,000 in this new account. Now there is a piece of this puzzle that we have forgotten to include. So not only when we start the new account are we putting $1,000 in at this particular rate. So we've upped how much money we're putting in. We've got a better rate than we started with. But we forgot the fact that that original amount, that $205,000 or $205,516.83 also got transferred to the new account. How do I incorporate that money being transferred to the new account? So I don't think I can use the formula that I just used. Because remember, this formula that we just used is for making payments. So you're paying yourself every month, right? If I was to use this formula and make that $205,000 be my R value, that says that I'm paying that much into my account every single month. And are we paying $205,000 into our account every single month? I mean, I would love if I was, but I don't think that's what we're doing. So what we're going to do, guys, is we're going to take this amount of money, this $205,516.83. I'm going to take this sum of money, or some might call it a lump sum of money, and I'm just going to dump it into this new account. Now notice, the fact that I use the phrase lump sum is super important. What does that mean? Oh, come on, guys, you got to talk to me. This is so important because this, a problem like this, your understanding of a problem like this is going to make or break this test. Where have we talked about lump sums before? Somebody. Don't make me start calling on people. I don't want to call on people.
Was it with interest?
So with interest, yeah. So what kind of interest though?
Simple?
Simple interest and also what? So we did simple interest, which was section 5.1. There was one other type.
Compound.
Compound interest. So simple interest and compound interest, which was 5.1 and 5.2, those deal with lump sum amounts. Section 5.3 and 5.4 deal with some type of payments. 5.3 is going to be payments to yourself in terms of a savings or retirement plan, whereas section 5.4 is going to be payments in terms of a loan. So because $205,000 is a lump sum amount, I have to go back and use one of the formulas from section 5.1 or 5.2. Now, 5.1 was simple interest, meaning we only compounded once a year. With this particular amount, if I put this $205,516.83, am I putting that amount, or am I only compounding that amount once a year? And the answer to that is no, because they tell us that our N is 12. We're compounding 12 times a year. I'm compounding monthly. So because I'm compounding something over once a year, that becomes a compound interest formula. So here, I'm going to take that amount that we just had here, and I'm going to plug it into the compound interest formula. And the compound interest formula says that we're going to have A equals our P, which is going to be that $205,516.83, times 1 plus R. So we're going to have 0.08 divided by 12 raised to the, what is it, NT? So 20 times 12. And if you multiply this out, you're going to get your A value here to be 1,000,000, what is this? $12,540.89. So that's the amount of money that putting that sum or lump sum into that second account is going to make. So we have this amount that the lump sum made. We have this amount that putting $1,000 into that account made. What do I need to do to these two numbers? I'm gonna add them. So our total in this account is going to be $1,601,561.31. That's how much money's in this total account here. Guys, again, I love this problem. This problem shows up on your project. This problem shows up on a quiz. It may even show up on a test. So make sure that you're comfortable with doing it.
Can we do another problem like this one from like the very beginning?
If we have time at the end of class,
Okay.
because right now I have got to get through the rest of section 5.3 if we're going to be able to study it all for your test. So if we, Shannon, if we have time, we'll come back to it.
Okay, thank you.
All right, guys, let's switch gears here, and I'm going to go look at, what do I want to do now? Let's go to page 371 in your ebook. Let's do a new share. All right, so now we've talked about, what was it they called it? Future value of the ordinary annuity. So guys, I told you last time when we looked at that particular formula, which was on page 369, and that was the formula that we just used to do half of that problem there. This is so important because your R is the payment at the end of each period. So it happens at the end. So we look for words like end of the period. So on 371, this is what happens when we talk about it being at the beginning of the period. So the formula developed previously is for ordinary annuities, annuities with payments at the end of each period. The result can be modified slightly to apply to the annuities due, which is annuities where payments are made at the beginning of each period. So you need to be sure that you are looking for that wording, either at the end or the beginning of the period, because it changes which formula you use. So our formula, and they show it like this: if you've got payments due at the beginning of the 3 years versus payments due at the end of the 4 years, you end up with an extra payment. So our formula ends up being this. So this is future value of an annuity due. We're going to have S equals R times 1 plus I raised to the N plus 1 minus 1 divided by I minus R. Again, I do not like the way they write this formula, so I'm going to write this in a little bit different format. And it looks like this. So we're going to have S equals R. R and S are still the same things. 1 plus I is actually R over N raised to the NT, so number of compoundings times time, plus 1. Then we do minus 1 from all of that over R over N, and then minus R. So that's the formula I'm going to use. Guys, it's the same thing. It's just your book defines I is your rate divided by your number of compoundings, and they define N, because they use N a little bit differently, as M times T, and M is your number of compoundings times your time. I've never seen a book that uses M for number of compoundings. So that's the formula that we are going to use. The biggest keyword here is beginning of the period. So the other formula is the end of the period. This one's the beginning of the period. Notice they look very, very similar to each other. So you're looking for that keyword here. So let's go through and do an example of this formula. So again, this is future value of an annuity due. So let's go look at page 374. So on 374, we're going to look at number 26. So notice in the directions here, they say find the future value of each annuity due. So with this particular section, they are telling you this is the formula that you need to look at. Now, what's going to happen as we go through this section, they're going to start throwing in more word problems. And with those word problems, we have to make sure that we're recognizing the words that suggest or tell us which formula we're supposed to be doing. So looking at number, well, 26 is boring. So that's compounded annually. Let's do 30. 30 is a little bit more entertaining. So we have payments of $750 for 15 years at 6% compounded semi-annually. So it's not super entertaining, but it's a little different. So remember, just like all the other problems, the first thing that we want to do is go in and identify what it is we know currently. So what do we know currently? So on number 30, what does that 750 represent? In terms of your variable. Trevor says R. You are correct, Trevor. That is definitely R. Okay, so what else do we know here? What's that 15?
RT.
That's RT, yep. What's 6%?
Little R.
That is little r. And finally, compounded semi-annually, what does that mean?
N.
Is, so if it's semi-annually, N would be
2.
2. Cool. So let's write down what we know on the whiteboard. And please notice, guys, I do this for every single problem because it helps us figure out exactly which formula that we are using. What do we have here? We had number 30. So we had R equals 750. We had little r was equal to 0.06, I believe. We had N was 2 because it was semi-annually. We had T was 15. So I'm going to plug this into the formula. So we're going to have S equals 750 times 1 plus 0.06 divided by 2 because it's R over N raised to the NT. So NT is going to be 2 times 15. But then you have to add 1 to it because that's the formula. And then we're going to subtract 1 from all of that value over 0.06 divided by 2. And then once we do that, I'm going to subtract 750 from it. So I'm subtracting a payment from it. So plugging it into the formula is not super complicated. Trying to get this formula plugged into your calculator is super complicated. So guys, I actually almost recommend you work your way inside out because it's easier to do. So, you know, if I've got my calculator here, the way that I'm going to do this is I'm going to do 1 plus parentheses 0.06 divided by 2. I close my parentheses. So that gives me this value here. I'm going to take that value and I'm going to raise that value to, and I can do this part in my head because 2 times 15 is 30. 30 plus 1 is 31. So I'm going to raise that answer to 31. So I get 2.5 something. I'm going to subtract 1 from this. So I get 1.5 something. I'm now going to divide. So we've done all this top part. I'm going to divide that by 0.06 divided by 2. Now I do put that in parentheses. So 0.06 divided by 2, hit enter. I've got 50 point something. So now I'm going to take that 50 point something. I'm going to multiply by the 750 here. So times 750. So I've got 37,000. And then from there, I'm going to subtract this 750. So I end up with S is equal to $36,752 and a penny. I will say this, it is much easier to type these things in on Desmos. Because on Desmos, you can see everything that you've got, and it's easier for Desmos to divide or put division symbols under things. On your calculator, you have to be super careful with parentheses if you try to type this in all at once. So any questions on that? So that is the value of an annuity due. So the future value of an annuity due. And we know it's an annuity due, and DUE is the due. Of course, my accent makes it hard to say due. Because the formula tells us this, but it's also at the beginning of the page. It's at the beginning of the period. So in the beginning, that's the 2 words that you need to look for. Okay, let's switch gears. Let's look at a word problem here, if nobody has any questions. Which one do I want to do? Let's look at number. Why are you not letting me move the mouse? Let's look at number 38. So number 38, a typical pack-a-day smoker in Illinois spends about $307.50 per month on cigarettes. I'm going to assume that that number is way off. Again, this book is very old. Suppose the smoker invests that amount at the end of each month in an investment fund that pays a return of 4.9% compounded monthly. What would the account be worth after 40 years? So how do we do this problem?
I'm a bit confused by the wording. Would you have to multiply the 307.50 times 12 to get the yearly, or no?
So here, so Milika, that's a really good question, and it really depends on what kind of account we're putting this into. So if it had said that we're gonna take this idea, because basically what we're trying to do is show that smoking, you can save money. The money that you spend on cigarettes, like put it into an account and actually gain money by the time you're done. So let's look at what kind of account they're putting it into. So if the smoker invests that amount at the end of each month in an investment fund. So because they're going to invest it at the end of each month and that investment fund is going to be compounded monthly, we don't want to take this and multiply it by 12. Because if I do, I'm going to switch everything over to yearly, right? And that's not what the problem wants it to be in terms of. It wants it to be in terms of months. Does that make sense?
Yeah.
Okay. So here, I believe that we're going to be using the ordinary annuity, right? The future value of an ordinary annuity, which is the formula before this last one. So let's try that one. So talk to me about what we know here. So what do we know on number 38? What's that $307.50 represent? Okay, let's try another number. What does monthly represent?
Your N,
Yeah, so our N is 12. We have 4.9%. What's that?
your rate,
Yep, that's our rate. And then of course, 40 years is our what?
time,
Time. So what's that 307.50 represent?
your big R value.
That's our big R value. Thank you, Shannon. Okay, so let's go to a whiteboard, write down everything that we just talked about. So on number 38, we have big R. So our payment is going to be $307.50. This is our way of encouraging people not to smoke. So little r is going to be, I think it's 4.9%. 38, 4.9%. So it's going to be 0.049. Our N, because it's monthly, is going to be 12. And then our time was 40 years. So we are going to have S equals big R, 307.50. And guys, with this in mind, we use the future value of an ordinary annuity a lot more than we use the future value of an annuity do. If they don't tell us what the pay period or what the period is, if they don't say it's at the end of the period, we assume it is. The only time we don't assume it's at the end is if they say, and well, actually, no, they say at the end of the month, don't they? Yeah, so they say at the end of the month. So never mind. So they do use the word "in," which means future value of an ordinary annuity. Okay. So what was I doing here? We've got 1 plus 0.049 divided by 12. We are going to raise that to the 12 times 40. And then I'm going to subtract 1, and then I'm going to divide all of this by 0.049 divided by 12. So if this particular smoker, instead of putting $307.50 a month on cigarettes, which like I said, I believe that cost is way higher, I don't know. How much would this person have saved over the course of 40 years? So by my calculations, this person has saved which is a nice little trip somewhere to buying cigarettes. Questions? All right, moving
I
right
have
along. Oh, go ahead.
So it's not really with the problem itself, like I understand that, but like how are you able to tell that this is like an ordinary annuity versus like any other type of like lump sum or compound interest formula?
Shannon, that is an amazing question. So let's go back and look at it. Because that's really where the confusion comes in all of this, as you're going through your homework and as you're going through quizzes and tests and stuff. So looking at number 38, do you see how we're making a monthly payment? Right, so this is what they pay by the end of the month. We're going to take that at the end of the month and put it into an account. So because it's a monthly payment, any type of lump sum formula is out. So I know it can't be simple interest. I know it can't be compound interest because those are lump sums. I have all the money at the very beginning and I just throw them into an account and don't touch it. Here, every single month I'm putting more money in. So that's how you know that it's not section 5.1 or 5.2. The reason that we know it's going to be this future value of an ordinary annuity is because you're putting it into a savings or an investment account. So when we get to section 5.4, 5.4 is going to be more along the lines of you're making payments on a mortgage. So you're actually bought something. These types of things, you're paying yourself money. That's what an annuity is. You're paying yourself that money. So that's how I know it has to be an annuity formula. And then we know it has to be the future value of an ordinary annuity because in the problem, they do say end.
Okay, that makes sense. Thank you.
Cool. Any other questions? Let's do another one. Let's look at let's do number 40. So on number 40, the Janus Enterprise Fund had, as of April 2013, a 10-year average return of 12.54%. Ooh, that's nice. If Elaine Chuha deposited $625 a month in the fund for 8 years, find the final value of the amount of her investments. We're going to assume monthly compounding. Okay, so this is what I was talking about a little earlier. If they don't say end, like the end of the month, we assume it's the end of the month. The only thing that we can assume is if it's at the beginning of the month. If they mean for it to be at the beginning of the month, they have to tell us it's at the beginning of the month. Otherwise, we just assume they're talking about the end because that's what most people do is at the end of the month. All right. So here we are depositing $625 a month. So we are making payments, or Miss Elaine here is making payments. So because she's making payments and it's payments that she's basically paying herself, right? She's doing this investment and that money's going to come back to her. So that's how I know that this is going to be the future value of an ordinary annuity. So if that's the case, what do we know here? So what's that 625 represent?
Big R.
That's big R, that's our payment. What does the 8 years represent?
Time.
So that's our T. What about monthly compounding?
N.
That's our N. And then of course, do we have our little r? Do we have a rate?
That 12.54%.
Mhm. Now notice, this is a 10-year average return. She's not doing it for 10 years. She's going to do it for 8 years, and that's okay. So let's go to a whiteboard. Let's write down everything that we just talked about. So again, we're going to do, I gotta get rid of this green. Let's do blue. So on number 40, and this is actually just part A, we know that our big R was 625. We know that our N is going to be 12 because it's compounded monthly. Little r was 12.54 or 0.54%, so 12.1254. And then we know our T is going to be 8. So she's only going for 8 years with this. So now if I plug it into that future value of an ordinary annuity, we're going to have S equals 625 times 1 plus 0.0125. No, 0.1254. 1254 divided by our number of compoundings, which is 12. I'm going to raise this to the 12 times 8. We're going to subtract 1. 12 times 8, that's a times. Subtract 1, and then I'm going to divide all of this by that 0.1254 divided by 12. So when all is said and done, what's our amount here that we end up with? So when all is said and done, we end up with, or Elaine ends up with, I wish I ended up with it, $102,442.33. So that's how much she ended up with in that account. And of course, we are not done because there is a part B. So let's go look and see what part B says. So part B says, if Elaine had invested instead with the Janus 20 fund, which had an average annual return of 10.63%, what would the final value of the amount of her investments be? Assume monthly compounding. So guys, here with this one, so she's investing the same amount of money. It's $625 a month. So that's big R. She's doing it for the same amount of time, which was 8 years. Compounding is the same. It's monthly compounding. So our N is 12. The only thing that we are changing on this problem is that 12.54% is going to change to be 10.63%. So my question to you is this: is she going to have more money at the end with this one or with part A?
With A.
Oh, definitely with A, right? You've got a 2% interest rate, or you got an interest rate that's almost 2% higher. So we're going to do everything all over again, except everything's going to stay the same, except for my little r is going to be 10.63%. So let me go back to my whiteboard. Which begs the question, why would she even worry about using this account? So again, everything's the same except for little r in this case is going to be 0.1063. So again, I'm going to write everything back out. So we got S equals 625 times 1 plus 0.1063 divided by 12 raised to the 12 times 8 minus 1 over 1063 divided by 12. Guys, if we run this calculation, we are going to end up with 93,967.67. So on part C, it just wants to know what's the difference in the amounts of these two accounts. So the difference in the amounts of these two accounts, I'm just going to take this value here. I'm going to subtract from it this value here. And if we subtract these two things out, the difference in this is going to be 8,474.66. If you're a millionaire, that's not a huge difference. If you're a teacher, $8,000 is a big, big difference. So I would definitely prefer account A as to account B. Questions on that one? All right, guys, I'm going to look at number 48. This will be the last problem we do in this section. I'm going to try to start section 5.4. Let's do a new share. So number 48. So Harvest Meats knows that it must buy a new machine in 4 years. The machine costs $12,000. In order to accumulate enough money to pay for the machine, Harv decides to deposit a sum of money at the end of each 6 months in an account paying 6% compounded semi-annually. How much should each payment be? That's different. So talk to me about what we know here. Again, I do see the word end. So because I see the word end, and I know this is an annuity because Harv's trying to pay himself the money so he can go buy this particular machine, I know that this has to be an ordinary annuity. So it's going to be the future value of an ordinary annuity formula that we're using. But guys, something weird happens here. How much money is Harv wanting to end up with?
$12,000.
Yeah, so that's, what does that represent?
The S.
Ooh, so this one's different because this time we have the final amount. We have the future value. We have S. So we're trying to find something different. So we know that S is going to be 12,000. He wants to buy this machine in 4 years. So that's going to be what?
Your time.
That's our T. Yep. Blah, 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 blah. So we're going to deposit a sum of money at the end of each 6 months. So 6 months, which means we're compounding semi-annually. So what's that? So compounding would be our N, and because it's semi-annually, that would be 2. So N is 2. Account paying 6%. So that's going to be our little R. That's going to be 0.06. That means that I am looking for big R in this problem. Let's go to the whiteboard and write down all of this stuff. So number 48. We know that S is equal to 12,000. We know that little r is equal to 0.06. N is equal to 2. T is equal to 4. So the thing that I am after here is big R. I have no idea what big R is. So if I set this up, I'm going to have 12,000 equals big R times 1 plus 0.06 divided by 2 raised to the 2 times 4 minus 1 divided by 0.06 divided by 2. So does anybody know how we're going to solve this? because I want that this time. So how are we going to go about solving this?
You could start by solving everything inside the brackets.
Yeah. So Shannon, you're exactly right. We are going to work everything out on that right-hand side. So I'm going to do the 1 plus 0.06 divided by 2. And then I'm going to raise that to the 8 because 2 times 4 is 8. I'm going to subtract 1 from it. And then I'm going to divide that point by 0.06 divided by 2. So let me go to Desmos and we'll talk about how we'll do this. Go away. Do a new share. Let's go to a different place. Where are you at? There you are. Okay. So we're going to have, what was it? It was, let me do a big parentheses here. We had 1 plus, do a little parentheses, 1 plus 0.06 divided by 2. And this is where Desmos is really nice because a calculator like a TI-83 doesn't really do that for you. And then we're going to raise that to the 8 because it's 2 times 4, which is 8. And then from there, I'm going to subtract 1. I'm going to close this parentheses. And then I'm going to divide all of this by 0.06. 0.06 divided by 2. So we end up with that number, right? So that's really what we're multiplying R by. So to finish solving this out, I need to take 12,000 and divide by that number. So I'm going to do 12,000 divided by, can I copy this number? You can tell I'm not an expert at this. Does anybody know how I could pull this number down on Desmos? Somebody? Anybody know?
You could just copy it.
It's not letting me copy it.
Oh,
for some reason.
mine did, so I'm not.
Oh, Shannon, you're cheating. Why does mine not? Because I feel like I should be able to copy that and it will not let me copy it.
Yeah, for some reason, Desmos doesn't let you copy and paste numbers. I haven't figured out how to pull it down. I usually just type in the exact thing, which is kind of time consuming.
That's dumb. There's got to be a way to do it. I just have to look it up. 4625. Okay. So with that being said, we end up with $1,349. Let's round off to 48 cents. So what happens is that's how much he needs to be paying every 6 months to make sure that he can afford this. So what were we buying? Just a new machine. Okay, so that's how much he needs to be putting into his account every 6 months to be sure that he can buy this new piece of equipment. I'm going to assume it's a meat slicer. I don't know. Anyways, okay, cool. So a little bit different take on what we were doing, and that's okay. So guys, that's the end of section 5.3. I am going to go ahead and start talking about section 5.4 just because I really want to make sure that we have time to at least do a review. That's my goal, is to do a review. So let me erase all this out. Go away, go away, go away. Let's go back to the book. And 376. So guys, when you think about payments, you think about car payments, mortgage payments, all of that stuff, that is going to be in section 5.4. So section 5.4 is all about annuities, present value, and amortization. Or amortization, however it is you say it. Me and my husband have a fight about which way you say it, and apparently both ways is correct. So in the annuities study previously, regular deposits were made into an interest-bearing account, and the value of the annuity increased from 0 at the beginning to some larger amount at the end because you were paying yourself. Now we expand the discussion to include annuities that begin with the amount of money and you make regular payments each period until the value of the annuity increases or decreases to 0. So examples of such annuities are lottery jackpots, which, guys, remember if you ever win the jackpot, because I tell students you have a better chance of being struck by lightning multiple times than winning a jackpot. But if you do, remember your favorite math teacher. So structured settlements imposed by a court in which the party is at fault. Or the party at fault makes regular payments to the injured party, and trust funds that pay the recipients a fixed amount at regular intervals. So these are payout annuities. So normally with the annuities that we've been doing, we've been putting money into an account to pay ourselves later on. This starts with the amount already, and we're just going to slowly dwindle out that amount. So let's talk about present value. So in section 5.2, we saw the present value of $8 at an interest rate I per period of N. So basically that's your R divided by your number of compoundings raised to number of compoundings times T, is the amount that must be deposited today in order to produce $8 in N period. Similarly, the present value of an annuity is the amount that must be deposited today at the same compound interest rate as the annuity to provide all of the payments for the term of the annuity. Does not matter whether the payments are invested to accumulate funds or paid out to disperse funds. The amount needed to provide the payments is the same in either case. So we're going to look at ordinary annuities. Okay. Do I want to do this? I don't think I want to do this. Look at the box on page 378. So here is your formula for the present value of an ordinary annuity. So again, with ordinary annuities, you do notice that your R is going to be the payment at the end of each period. It's annuities due that's at the beginning. The I is the interest rate per period, and N is the number of periods. Of course, I'm going to give you this formula in a way that is not quite as confusing as what they have. So here's our formula. Our formula is going to say P equals R times 1 minus 1 plus R divided by N raised to the negative NT over R divided by N. So we are doing a negative NT, guys. When I was working on your project, I kept using this formula, and I don't know why. I kept forgetting to put the negative. So don't forget that with the present value of an ordinary annuity, you do need that negative number, or you need that negative on your NT. So that's the formula that we are going to be using. Again, same formula. I just think it's a lot easier with the R's and N's in there. Now, there is this really cool note down here that says, do not confuse the formula for the present value of an annuity with the one for the future value of an annuity. Notice the difference. For this one, which is the present value, we're doing 1 minus this value. The other one, we're doing basically this value without the negative minus 1. So where the minus is, it differs. So that's our formula. Okay, let's go do a super quick example of this. So I'm going to go on to page 385. And we are going to look at problem number 2. So notice with these, they do give you the directions, which is super nice. When you have the directions, you know exactly which formula you're supposed to be using. When they start putting them in word problem format, though, that's when it gets a little confusing. So number 2, we have find the present value of the each ordinary annuity. So we've got number 2, we've got payments of $890 each year for 16 years at 6% compounded annually. Guys, again, this is just a plug and chug. We figure out what we know and we plug it in and go from there. Let's erase our formula here. So payments of $890 per year, that's going to be your big R. We're doing it for 16 years. That's your T. 6% is going to be your little r, and compounded annually is going to be your N value. So our N is going to be a 1. So not a super entertaining formula here. So let's go to a whiteboard. Clear this out. So on number 2. we have that big R is equal to 890. We had that N was going to be 1 because it was compounded annually. We had little r was equivalent to 6% or 0.06. And our T was going to be for 16 years. So if I plug this into the formula, we're going to have P equals 890 times 1 minus 1 plus 0.06 divided by 1 raised to the negative, don't forget that negative, 16 times 1 divided by 0.06 divided by 1. So I really don't need to divide it by 1 or the multiplied by 1. So at this point, this is just a plug and chug formula. We punch it in. We end up with P ends up being 8,994.25. All right, cool. Guys, again, this formula is just plug and chug with these. I do think I want to show you number 10. Well, let's do a new share here. So I've got a note about number 10. What's number 10 say? Number 10 says, find the amount necessary to fund the given withdrawals. Monthly withdrawals of $425 for 10 years, interest rate is 6.1% compounded monthly. Okay, I know why I mentioned this. Guys, here's what happens. You remember that statement I read just a little while ago that says it doesn't matter if you're paying in money or pulling out money, it's the same formula. That's what this is saying. So here, even though we're making these withdrawals on number 10, you're still doing the very same thing that you did back in number 2. So with number 10, even though the money is coming out, it's still going to be you're making withdrawals of $3,500. That's your big R. T is going to be 7. Little r is going to be 0.052. Your N is going to be 2. So with this section, at least with the annuity stuff, it doesn't matter if you're putting money in or you're taking money out. It's still the same exact formula. And that's what that note that I read you was. So I'm not going to do 10 because it's the very same thing, but just be aware that it's the same formula that you're using. All right, guys, so when we come back, I'm going to pick up number 12. So we'll look at number 12 and I'm going to try my best to, I want this chapter done on Tuesday. So we're going to have to push it to get it done on Tuesday, but that's what we're looking at doing on Tuesday. Guys, I would say you have homework due in the context of 5.3, but everything opens back up next week. So you're not technically going to have any homework due on Tuesday because everything will be back or open back up. So have a wonderful weekend and I will see you again on Tuesday.
I have a quick question
Thank
about
you.
the final exam.
Yes.
I was wondering if it was going to be similar to other exams we've taken or if it would be more multiple choice.
No multiple choice.
Okay, I was just wondering. Thank you.
Mm-hmm.